Good morning. Welcome to Krishna's classroom. Last time I gave the details of the proof of the implicit function theorem as an application of the fixed point theorem. Now, you have already seen the details of the proof, and as concluding remarks, I said with that we conclude the lectures on metric spaces. Later on, I thought that possibly a short remark on the geometry of the proof may be worthwhile to get some insight into the application of the fixed point theorem. So this short lecture is an attempt to do that. Okay, just recall what we were looking at this problem. We wanted to solve this equation, y as a function of x in the neighborhood of a point x naught, y naught. Of course, f is from u contained in R2 R. We make some assumptions on, there are conditions on f, and this is a point in u, and we have assumed that fx, fy are continuous. On these are the partial derivatives. And then we have the statement of the implicit function theorem, which I don't want to recall again. And while proving this theorem, first, what we wanted to prove is this, that there exists a epsilon positive such that on epsilon we can find G. Continuous and sufficiently smooth such that f of x gx equal to 0 for x belonging to this is what we wanted. That is, you can solve this equation in this form, where of course you have gx naught equal to now we assume g is, say, a continuous function with continuous derivative. Okay. To recall the proof, what we did was we constructed a function f of y minus inverse f of xy, and we had assumed that okay, 0. So that this is well defined. Then of course we did some, so the problem is this, something like this. So you have this x0, y0. This is your u. U need not be a bounded to, can be unbounded. So I'll just some part of this so that it should be even unbounded. Need not be the whole of R codes. Now you can find a rectangle with x0, y0 at the center. Something like this rectangle is this length is delta 1, delta 2, delta 2. So this is the point x0. Now we fix delta 1 and delta 2 such that some conditions are satisfied by f and its partial derivatives. Okay. So specifically the sort of conditions we had was, suppose I call this rectangle say R. Suppose R is mod x minus x0 less than or equal to delta 1, mod y minus y0 less than or equal to delta 2. Then we had f of x0 y0 equal to y0 further equal to 0, and the way in which we have chosen delta 1 and delta 2 are such that df by dy on the rectangle R. These are the assumptions that we made. Then we reduce this whole thing into a fixed point, into a situation where you can apply the fixed point here. What did we do? We defined x to be a set of all g belonging to is a continuous function on delta 1 with condition that g x0 equal to y0 and gx y0 is less than or equal to delta 2 if mod x minus x naught less than delta. Okay. So this collection was designated by X. X is a space, is a vector space of continuous functions defined on the interval x naught minus delta 1 to x naught plus delta 1. No, I'll correct it. X is a metric space of continuous functions defined on the interval x naught minus delta to x naught plus delta with gx naught equal to y naught and mod gx minus y naught less than or equal to delta 2 if mod x minus x1 delta 1, which simply means the following. I will draw the geometry. What is x? Okay. You have the point x naught, y naught, and then you have the rectangle. This is the rectangle R. This is the rectangle R, which is given by mod x minus x naught. So R we have already defined here. So this is the definition of R, and therefore this is delta 1, delta 2, delta are these, and this is the point x naught. Now you are talking about all continuous functions defined on the interval mod x minus x naught less than delta 1. So let us say it is the x-axis, maybe here or it depends on the space. This is x naught minus delta. This is x naught plus delta 1. This is the interval that we are considering. Now the conditions say that you have a continuous function. A typical member of this collection x is a function that is continuous on this interval passing through the point x naught y. So all those continuous functions, so the graph is something like this. So that, see, these are all the functions. It's also a bundle of fibers held tied up at this point x naught y naught, so that all these curves pass through this. This is the collection of curves, and this collection of curves is each curve belongs to the collection x, and this particular collection constitutes a metric space. And we have already seen that with the supremum distance that we have defined, x is a complete metric space. That's what we have seen. Now what have we proved? We defined T G to be f of x gx. That means for each function having a graph like this, we have defined Tg of x. What do you get through this? This is how we define it, f x gx. Therefore, you produce another function of x defined on the interval x naught minus delta to x naught plus delta. So you see that x is a complete metric space. So what you could prove is the following, that T is a map from x to x. If it has to be from x to x, what all things it should satisfy? We have proved Tg at x dot equal to y naught, so that the image of G under T is another curve passing through this. So it's something like this. I just displayed. So this is, suppose this is G, this is T. So Tg is a curve, another curve defined on the interval x naught minus delta 1 to x naught plus delta 1, which has the property that Tg at x naught is equal to y naught, or in other words, the graph of the function Tg passes through the point x naught. Okay. Now you can show that T is from x to x having this property. So in particular, you have to prove this. Okay, so that it's from x to x. So this is a crucial part of the proof. Okay. Now also it said that because of the second condition that we have put, namely that G, what is that? Gx minus y naught, modulus of that is less than or equal to delta 2, which ensures that the graph of the function is confined to the graph of the function rectangle. So what we have is that you are now defining a function on the metric space, on the complete metric space of all continuous functions on the interval x naught minus delta 1, x naught delta 1, and passing through the point x naught y naught with certain bound fixed, so that the graph of such functions stay in this region R. Okay. So that is done. I mean, that's these steps we have already done. Now, what one proves further is that T is then a contraction. Under the given conditions, that is norm of or the distance of is less than or equal to half of the distance from okay. So here the distance is calculated as the difference of these functions, and then so distance of GH. So that is the definition. Then P is a contraction and hence by the fixed point theorem, contraction mapping PG equal. And then this becomes what is called the solution of this implicit function problem. Okay, right? And therefore, what you get is that F equal to 0 and so this is the solution of the implicit function problem. Okay. So I think that gives the explanation. Actually, this picture or this graph graphic representation of x, and the objects on which the operator t is defined consists of all continuous functions on the interval x0 minus delta 1 to x0 plus delta 1, which passes through the point, whose graph would pass through the point x0. Okay, now this is the geometry of the proof. I thought that maybe it is worthwhile to spend a moment on the geometry, so that there is better clarity on how the fixed point theorem lies. So thank you very much.